Double check that we are live. It looks like we are. Good evening, good evening. I hope your week is off to a good start on this Monday. I was actually planning on starting much earlier than this, but then I sat on my couch in my office and I don't know why I got sucked into watching some Kubernetes stuff. Yeah. Anyway, so yeah, let's try and get some reading in. I didn't want to skip because I'm really trying to finish the let me see, what is it? This whole section of the manual called writing reactors. Basically, it's, giving you your introduction to all the important mechanics of the Lingua Franca language and its runtime. So my hope is that we can get through, from deadlines all the way to termination for this week. So I didn't want to miss tonight. Yeah, so I guess let's just jump right in. So last thing we did was modal reactors, which is super cool. The idea that you can have your reactor operate in multiple modes, and how that basically the implications of that in terms of state transitions and all that. So that was super cool. Now today we are starting with deadlines, and as the name implies, I haven't read this yet, but I think this is more of the real-time aspects of embedded systems that this language is also targeting, like that domain of having embedded writing software for embedded systems where you need some real-time semantics or guarantees at runtime. So I think that's why the deadline stuff comes in. Alright, so Lingua Franca includes a notion of a deadline, which is a constraint on the relation between logical time and physical time. Specifically, a program may specify that the invocation of a reaction must occur within some physical time interval of the logical time of the message. Let me try that again. Specifically, a program may specify that the invocation of a reaction must occur within some physical time interval of the logical time of the message. Okay. Yeah, and I think, logical time is definitely not necessarily physical time. But I think I remember we read somewhere in the manual that it's often the case that logical time is trailing behind physical time. So in this case, a deadline would be that you basically want to limit the amount of lag between some logical time and the running physical time. Okay, so if a reaction is invoked at logical time 12 noon, for example, and the reaction has a deadline of 1 hour, then the reaction is required to be invoked before the physical time clock of the execution platform, which is 1 p.m. If the deadline is violated, then the specified deadline handler is invoked instead of the reaction. Okay. The reaction has a deadline of 1 hour. So even though the logical time is 12, the deadline is relative to the expected, or the target deadline time is expressed in actual physical time. Okay. Purposes of deadlines. A deadline in an LF program serves two purposes. First, it can guide scheduling in that a scheduler may prioritize reactions with deadlines over those without, or those with longer deadlines. For this purpose, if a reaction has a deadline, then upstream reactions on which it depends without logical delay inherits its deadline. That makes sense. Hence, those upstream reactions will be given a higher priority. Second, the deadline mechanism provides a fault handler, a section of code to invoke when the deadline requirement is violated. Because invocation of the fault handler depends on factors beyond the control of the LF program. An LF program with deadlines becomes non-deterministic. The behavior of the program depends on the exact timing of the execution. There remains the question of when the fault handler should be invoked. By default, deadlines in LF Lingua Franca are lazy, meaning that the fault handler is invoked at the logical time of the event, triggering the reaction whose deadline is missed. Specifically, the possible violation of a deadline is not checked until the reaction with the deadline is ready to execute. Only then is the determination made whether to invoke the regular reaction or the fault handler. Deadline specification. So this is saying 10 milliseconds in terms of real time. If it's been 10 milliseconds in real time since the logical time at which this reaction, would it be the reaction or the X? I feel like it'll be the X, right? So 10 milliseconds in terms of real time since the logical time at which the input X should have triggered a reaction. That's how I read that. And so this is the actual reaction and this is the deadline. This reactor specifies a deadline of 10 milliseconds. This can be a parameter of the reactor. If the reaction of X is triggered later in physical time, if the reaction is triggered later in physical time than 10 milliseconds past the time step of X, then the second body of code is executed instead of the first. The second body of code has access to anything the first body of code has access to, including the input X and the output D. The output can be used to notify the rest of the system that a deadline violation occurred. This reactor can be tested as follows. Wait, which one? Okay, deadline. Deadline enough is imported. Preamble. Main reactor, logical. Action A. Okay, so we instantiate this. Okay, so the startup trigger for the reaction, which is expected to have some side effect on the deadline reactor at X and the logical action A. And this is the implementation. I see. Okay, so this is the thing that. Okay. So this happens, which is gonna trigger this, which will reset again. Set it to 0, and it's gonna sleep for 20 seconds. Well, 20 milliseconds. Sorry. And if I'm understanding this right, the side effect of this won't happen until after the 20 millisecond sleep, which would trigger the deadline here. So, if I remember correctly, yes, I believe this is in fact the case. Reactions are transactional, meaning that even though this, in this reaction block, you're setting X before you're invoking the sleep command here, all of this is assumed to happen simultaneously as one atomic change. So this reaction side effects won't actually be applied until this 20 millisecond pause or sleep has taken place. Excuse me. And this reaction here is gonna react when the deadline reactor has its deadline handler update the output channel here. Um, yeah. Excuse me. Running this program will result in the following output. So you have the normal reaction. Wait. Wait. How does. Why does this run? Oh, because on startup. Yes. Okay. On startup. Um. On startup, this happens. So the deadline reaction here does run the first time. But then the scheduling here causes a slip of 20 milliseconds the second time around, and you get the violation. The first reaction of the deadline reactor does not violate the deadline, yes, but the second does, indeed. Notice that the slip in the main reactor occurs after setting the output, but because of the deterministic semantics of LF, this does not matter. Yep, that's what I was talking myself through just a few seconds ago. The actual value of an output cannot be known until every reaction that sets that output completes its execution. Oh, it's actually much more rigid than I thought. It's not just that this reaction on the side effect like if there were other reactions that are triggered and have side effects on the X, like if you had another reaction that had A as a trigger, then not only will this need to finish running, including the 20 millisecond slip, but that other reaction will also need to run to completion. So if that one, let's say, had another, I don't know, 100 milliseconds, then we'll have to wait another 100 milliseconds before we know what dx actually becomes. Well, actually, no, we wouldn't have. We will actually have to just wait for 100 milliseconds. It's not because the second one will override this one. So instead of 120 milliseconds, it will just be 100. It's last right wins. It's a yeah, can't talk. It's the principle of last right wins. It's common in many distributed system stuff to resolve consistency issues. Yeah, so since this reaction takes 20 milliseconds to complete, the deadline is assured of being validated. Yeah. Notice that the deadline is annotated annotated, annotated, annotated in the diagram with a small clock symbol. Let me see. Oh, okay. Yeah, that deadline. Notice that the deadline violation here is caused by an invocation of LF slip defined in platform H. C libraries available to programmers. It is not generally advisable for a reaction to slip because this can block other reactions from executing. But this is exactly what we are trying to accomplish here in order to force a deadline to be violated. Deadline violations during execution. Whether a deadline violation occurs is checked only before invoking the reaction with a deadline. What if the reaction itself runs for long enough that the deadline gets violated during reaction execution? Wait. I don't think. Oh. Okay. Actually, had not considered that. You can have a reaction that runs for so long that it actually violates its own deadline, which I guess makes sense if you're thinking in terms of real time stuff, or if you're writing some sort of runtime verification tool of some kind, and you want to have strict boundaries on I guess latency and by proxy throughput. Right, because if you know that you only have a budget of I don't know how many milliseconds, then physically, or at least mathematically speaking, there's only so much data that you can actually process during that specific window of time. And if you don't know it, it's a matter of trial by error, and you can just experiment with a given range. So yeah, I guess for both latency but also throughput, you can leverage this feature for that to enforce some latency or throughput policies at runtime. Anyway, for this purpose, a target language function is provided to check whether a deadline is violated during execution of a reaction with a deadline. Okay. So this is a while loop that will keep running as long as the deadline is not violated. But once it is, it sets the count. Oh, but if it's valid, okay, yeah, if it's validated, this will still be run, which is yeah, it's interesting because I can see an angle where you could argue that to simplify matters of state consistency, you could make the argument that when a reaction during execution runs out of time, aka deadline violation, then you cannot commit any changes that were made um, as part of that reaction. I mean, that would completely eliminate the chance of um, committing partial state that can have un- unforeseen consequences, um, either immediately or after the accumulation of, steps in a state machine. So again, I mean, if we look at it from a database standpoint, um, when you're running a transaction, and let's say you have a timeout set, and if that timeout is reached, the transaction doesn't go ahead and commit the work that it has done as a work in progress. It's as if it never happened. I mean, obviously that means you just literally wasted um, time and the machine resources to run the request. But at least you know that you know that you're not committing a partial state. Now this, but then you also have to consider that um, if you have a durable execution semantics to work with, then maybe committing partial state is actually not that terrible. You could, in fact, in some cases, it may actually be what you want, so that the next attempt that you make, you're not starting from zero. You're starting from a partial state that that gives you a much better chance at finishing the task in question or the procedure in question. And based on that behavior, after doing some fine tuning or whatever, then you can properly partition or size the workload instead of trying to do the whole thing in one go or in one single reaction. You can split it up into multiple reactions, each one taking the maximum allowed time frame to run, and they just kind of sequentially even maybe in parallel, depending on what the work is. Basically divide and conquer. So yeah, this will be something that forces you to divide and conquer if you're trying to meet very specific latency and throughput requirements. The count reactor has a single reaction with a deadline of 3 milliseconds. If the deadline is not already violated when this reaction becomes enabled at startup, then the reaction begins executing the loop. In each iteration of the loop, it calls this, which returns true if the deadline has been violated and false otherwise. Hence, this reaction increment the count variable as many times as possible before the deadline is violated. And at that point, we'll exit the loop and produce on the output the count. Running this program will produce something like this. Okay, stop counting. So it's not very the transactional, the typical database, I should say maybe relational SQL database transaction semantics are not the same. Are different from what's happening here, in the sense that here you get to commit whatever partial work you've done, right? So this reaction kept incrementing the count. And once it exited the while loop, because, time's out or time's up, it committed its partial work. And yeah. This is a rather trivial example of an anytime computation. Such computations proceed to improve results until time runs out and then produce the most improved result. The argument to the check deadline or the self-struct. Okay. Excuse me. Actually, I wonder what that is like for, I don't know, Python. Is that also okay, it's only implemented in C. Okay. Alright, let's go to multiports and banks. Oh, it's a long one. Alright. Let's try to power through this. Lingua Franca provides a compact syntax for ports that can send or receive over multiple channels, and another syntax for multiple instances of a reactor class. These are respectively called multiports and banks of reactors. Banks of reactors. Feels like, if you think of a reactor as a thread, then banks of reactors basically is a thread pool. But I don't think that excuse me. Obviously, I don't think that it's, and it's not by default. I don't think each reactor, at least, thinking about the runtime of this language, I don't think that by default, in fact, I don't even know if that's actually a feature of the runtime, but I don't think that one reactor equals one OS thread. Maybe one man reactor. I don't know, actually. I don't know enough about the internals of the runtime, and I don't think they haven't talked about how threading and concurrency works in this runtime. Okay, yeah, multiports and banks of reactors. Multiports. To declare an input or output port to be a multiport, use the following syntax: input, output. Okay, where width is a positive integer. This can be given either as an integer literal or a parameter name. Consider the following example. output 4. Reaction. Okay, into iter enumerate. Okay. So if you think of an output as a channel, then this is basically creating 4 channels. Here you have input. So 4 inputs. So source destination. Okay, so these 4 are going to be sent to the destination. Also, okay, so I guess when you interact with the input here, you always have to interact with it as a set. Like you can't just I guess what I'm trying to say is you just treat it the way you would treat a cluster of, I don't know, a cluster of nodes. Like it's a cluster of something. Like, I don't know. Don't they say pets versus cattle? This is definitely a cattle situation, I think. Anyway. So, this is pretty straightforward. The output here goes into the input there. I want to wager the fact that the cardinality of the out port and the input port must be the same. Like if you're gonna connect multi-ports, I think. Okay, but because if it's not the same, then for determinism, do you have to ensure that you have a very specific mapping between the like each member of the output channel here to each member in the input channel here? Like here we have 1 2 3 4 1 2 3 4. Well, okay, let's assume that this was actually 1 2, just a cardinality of 2 here. Then how do you deterministically say that those 2 will always match to the first 2? Actually you can do that pretty naively and basically force people to just get on with it, because it's the most stupid simple approach, which is it goes by the order it goes by both the order of the declaration and the remaining list of the destination reactors multiports. Yeah, I don't know. Let's just read on. That'll probably answers to my question here. Executing this program will yield, okay. The source reactor has four-way multi-port output, and the destination reactor has four-way multi-port input. These channels are connected all at once on one line. The second line from the last. Oh, yeah. Wait, what? These channels are connected all at once on one line. The second line from the last. They mean this is the second line. I mean, as the last line. Seems like that's what they meant as the last line. I will think of this as being the last line. But anyway, okay, whether it shows the width is controlled by an option in diagram generator. The source reactor specified out as an effect of its reaction using the syntax out. This brings into scope of the reaction body a way to access the width of the port and a way to write to each channel of the port. In destination, the reaction is triggered by in, not by some individual channel of the multi-port input. Yeah, that. I guess that's where the cattle thing comes in. Like, it's not, you can't have a reaction that gets triggered only on, let's say, the third element. Like, you can't index into the multi-port so that you can only select a subset as triggers for a reaction. And that's my understanding of this. Hence, it is important when using multi-port inputs to test for presence of the input on each channel, as done above. Yeah, this is how it's checked here. Parameterized widths. The width of a port may be given by a parameter. For example, the above source reactor can be rewritten. That's pretty nice, actually. I wonder if they have the zig feature of comp time, because you can then have comp time parameters. I feel like that would be a nice feature to have for parameters, because then something like this you may not have to hard code it like that, and just have something that is set via a compilation flag or some environment variable or whatever that gets passed in at compile time. Okay. Connecting reactors with different width. Alright. Assume that the source and destination reactors above both use a parameter width to specify the width of the ports. Then the following connection is valid. Excuse me. So I think, okay, yeah. So you can have multiple sources into the same destination, but at different um, ports within the multi-port. But I think the rule is probably that as long as the entire destination's multi-port is filled, then you're good. But I also wonder if this is equivalent to also having A2 out and then A1 out. Basically, permuting the position of this and this. Like swapping the position and keeping everything else the same. Would that produce the same? I mean, is that deterministic? Hmm. Okay. The first three parts of B will receive. Oh, will receive. I don't think we need the ED here or the D here. The first three parts of B will receive input from A1, and the last two parts will receive input from A2. Parallel composition can appear on either side of a connection, for example. Wait, so you have A1, A2, then you have B1, B2, B2. Oh, but then that's just you. Um, yeah, basically you are duplicating links. So it's really this, then this, and this. You're basically collapsing three statements, three of these into a single statement. Okay. If the total width on the left does not match the total width on the right, the total width, okay, then the warning is issued. If the left side is wider than the right, okay, if it's wider, then it needs to find another destination. But I don't know if that's actually considered a bug. Let's see. If the left side is wider than the right, then output data will be discarded. Um, okay. So basically, yeah, okay. Wasted, discarded, because it has nowhere to land as a destination. If the right side is wider than the left, then input channels will be absent. Okay. Um. Oof. I just felt like the garbage collector just ran in my head. If I mean, this is just a reference to the whole the common thing that people complain about when it comes to garbage collection, where it's like sometimes while the program is running, you have this quote unquote pause of the world where the garbage collector basically takes over and nothing else really gets to run, and that can cause unexpected latency or just overall performance issues where things just stall for no immediately apparent reasons. Any given port can appear only once on the right side of the arrow connection operator of the connection operator. So all connections to a multiple destination must be made in one single connection statement. So again, I mean, yeah, you can't. Once you have a multi-port, you can't. You have to treat it as a single atomic block component. Banks of reactors. Using a similar notation, it's possible to create a bank of reactors. For example, we can create a bank of 4 instances of source and 4 instances of destination and connect them as follows. Excuse me. Trying to get my camera to readjust a little bit. Alright. Let's power through this. My mouse is doing the thing again. Gosh. Okay. Okay, so banks of reactors. So in this example, we have 4 and 4. Okay, so they're all like that. There are 4 of them. Wait. Oh, okay. So here you're combining them. So you have 3 instances, and for each one, you have a multiport with a cardinality of 4. And for destination, you have 4 of them. So there's one too many, that is compared to the source. And in terms of the multiport size, there's one less. So here, because there's one less, gosh, what was it? I think in this case you'll get a warning, right? Yeah, I think. There will be 3 instances of source, each with an output of width 4 And for instance, the destination with each with an input of 3 for a total of 12 connections. Excuse me. To distinguish the instances in a bank of reactors, the reactor can define a parameter called bank index. Okay. With any type that can be assigned a non-negative integer value. If a parameter is defined for the reactor, then when the reactor is instantiated in a bank, each instance will be assigned a number between 0 and n minus 1, where n is the number of reactor instances in the bank. So this is a built-in, like, reserved parameter then. For example, the following source reactor increments the output it produces by the value of bank index on each reaction to the timer. So here's the timer, and I believe this means that there is a 0 delay relative to the startup time. And then this is saying 200 milliseconds from after after the delay amount has elapsed, in this case being 0. So this will be 20 milliseconds after startup. We get this. Okay, so the width of a bank may also be given by a parameter as in oh, you can also do it on the main reactor. That's cool. But I guess what I'm wondering is, are these actually like predetermined parameters? Like, what if I just want to write it as SLC instead of source? Then I guess it will just recognize it as a custom parameter thing. Like, I'm basically trying to figure out if these are like special and well-known parameters to use, or they're just made up like all the other ones and it's mostly just convention. Okay, so this is all about parameters, leveraging them. Contained banks. Banks of reactors can be nested. For example, know the following program. That's some Inception stuff right there. So you have 2 instances. At default, the first one will be 0, the other one will be 1. So now we have 2 here. This will actually yield a total 2 times 2, because we have 2 parents. So 2 child per parent. Per parent. Adding the child. using a parameter to initialize a state. Okay. So in terms of bank index, so you'll have 0, 1. So bank index, okay. Oh, yeah, okay, 4 child instances. So 0 to 1. So this will be, yeah, anywhere from 0 to 3. Oh, oh, I made a mistake. Uh, oh, wait. Because it's for each separate one. Okay. In this program, the parent reactor contains a bank of child reactor instances with a width of 2. In a main reactor, a bank of parent reactors is instantiated with a width of 2, therefore creating 4 child instances. In the program, in total, the output programming will be 0101. The order of these outputs will be non-deterministic if the execution is multi-threaded, which it will be by default, because there's no dependence between the reactions and hence they can execute in parallel. The bank index of a container reactor can be passed down to contain child reactors. Oh. Okay. Two instances of parent means 4 instances of child. The indexes will be 0 and 1, which gets passed. So you have 0, 1 and 0, 1. Zero, 1, 0, 1. So 4 child. And for each one by default the thing goes in, so that's 0, 1, 0, 1, 2. And then the parent thing comes from here. Wow. From the bank index, which is also 0, 1. Yeah. And the output is not deterministic. Okay. Finally, members of contained banks of reactors can be individually addressed in the body of reactions of the parent reactor if the input-output port appears In a reaction signature, for example, know the following program. This is 1, 2, 3 from child 0, 1. Not very clear on this particular last part here, but I'm gonna move on because I don't want to get stuck in the middle of this page when my brain decides to just short circuit, which is not long now. And by that I mean, obviously, sleep. Combining banks and multiports. Banks of reactors may be combined with multiports as in the following. Okay, didn't we just go through this up over there? So that info destination. Oh, combining banks and multiports. So this one is only one thing, but it has multiple ports, and then you can pipe that into 3 different receivers or receiving reactors. It should be banks of reactors, I guess. Okay. Mm, mm, mm. Mm, mm, mm. Okay. Don't know why it took me 10 seconds to review that. I just realized that it did. The 3 outputs from the source instance will be sent respectively to each of 3 instances of destination. The result of the program will be something like this. Destination 0, destination 1. Created A out. So start up. There's that. The order of non-determinism is, well, the order is non-deterministic in a multi-threaded context. That makes sense. The reactors in a bank may themselves have multiports. In all cases, the normal ports on the left of a connection must match the number on the right, unless the ones on the left are iterated, as explained next. Wait, what? Iterated? What does that mean? I mean, I know what it means literally, but within the context of this, I'm not sure I know what it means. In all cases, the number of ports on the left of a connection must match the number on the right. I mean, yeah, that specific part sounds fine to me. It's this part that I'm not quite sure yet. Unless the ones on the left are iterated. Huh, okay. Still don't quite understand what they try to say there. Let's see. Excuse me. Occasionally, you would want to have fewer ports on the left of a connection and have the outputs used repeatedly to broadcast to the ports on the right. Okay. In the following example, the outputs from an ordinary port are broadcast to the inputs of all instances of a bank of reactors. Threaded. That's funny. Anyway, feels very Java-esque. Anyway, takes in the parameters with the default value 4. So we have a source width. And the destination. So this is the magic. The syntax means, this syntax here. Wow, the whole thing really. The syntax means repeat the output port A out one or more times as needed to supply all the input ports of the in destination in. The content inside the parentheses can be a common separated list of ports. The ports inside can be ordinary ports or multi-ports, and the reactors inside can be ordinary reactors or banks of reactors. In all cases, the number of ports inside the parentheses on the left must divide the number of ports on the right. Man, I am fading fast. It's a good thing we're almost there. Oh, we are here. Until if it's not supporting this target, so I'm guessing it's not supporting in Rust. It's probably only supporting in C or C++. Oh, they have a much longer thing here. I think we made it up to here. So now we have interleaved. Interleave connections. Sometimes we don't want to broadcast messages to all reactors, but need more fine-grained control as to which reactor within a bank receives the message. If we have a separate source and destination, if we have separate source and destination reactors, this can be done by combining multiple ports and banks, as was shown in combining banks and multi-ports. Setting a value on the index n of the output multi-port will result in a message to the nth reactor instance within the destination bank. Okay, yeah, I can dig it. I think we sort of already rambled on about the whole matching and indexing thing. However, this pattern gets slightly more complicated. If we want to exchange addressable messages between instances of the same bank. Okay. I'm not reading through all that right now. Not gonna lie. I'm trying to make it to the finish line here. In the above program, 4 instances of node are created. And at startup, each instance sends 42 to its second. Let me see this. Okay, so this is the input. Okay. Indexing for a very specific node. I guess port in the multi-port. The result is that the second bank member, bank index 1, will receive the number 42 on each input channel of its multi-port input. Sorry, I just wanted to double check something. Gosh, there was one thing that I wanted to double check. And then the garbage collector just ran. And I lost it. Gosh. Okay, well. So this is the source. They were sending it to this one port, the 42 one. And that destination has actually 4 output, right? This. Yeah. I feel like we can skip this last part. In the grand scheme of things, I don't think that this is something that we have to go over at this point. And that's my excuse for basically wanting to pause on this chapter, or pause and resume tomorrow with the next chapter. That was a lot. The deadline and the multi-ports and banks. The multi-ports and banks has to be one of the more that. Well, actually, I guess all of these. But I mean, yeah, I think this four here probably are definitely some of the most important features of this language slash runtime. Anyway, yeah, we'll stop here. We'll stop reading this chapter, and tomorrow we'll get started with generic reactors. Should be straightforward. This is just generics. Let's see. Do I have the presence to do some ontology reading right now? I don't know. Oh my. Oh my. Oh my. I don't know. I don't know if I have some reading in me right now. Oh, you know what? Let's quickly look at something. I think there was something that. Ooh, that's interesting. This is test. is. Suppose that there's no seed passed in here. Oh, maybe it's already. Yes, maybe it's already set up when as a flag whenever you run the actual test pipeline. Oh, yeah, it is. Simulator. Devoted Ahmed. Indeed, I am devoted, and I am Ahmed. So, assume starts initially from an empty database. Actually, you know what? Let's do the ontology thing. It's not that I don't want to do this, but then it's a matter of, well, if you're gonna do that, then you should just stick to what you plan on doing in the first place. So let's do that. Instead of looking at limbo simulator code thing, which we'll do at some point. Oh. Okay. Standing up should help. Alright. Ontology aware applications. Foundry contains a number of applications developed to operate natively on top of the ontology. Together, these object-aware applications deliver powerful analytics and operational platform that supports a range of use cases and user profiles. To learn more about why setting up an ontology and using object-aware applications is valuable. Which page is that? Oh, we already read it. This page provides a reference to the available applications and explain when you should use each application reference. Object views. Our essential hub for all information and workflows related to a particular object. My neck. Been killing me all day. Okay, this includes key biographical data about an object, and a linked object, key related metrics and links, blah 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 blah. For example, the airport object type, object view might provide the following information for each airport object: country, latitude, city, management console, timeline. Okay. Biographical data, 6-degree view of all aircraft objects and flight objects. Link to the airport. Okay, Object Explorer. In a search and analysis tool for answering questions about anything in the ontology layer. Oh, that is not in. Users can visually compose search queries ranging from simple filters to search arounds to find objects of interest. From there, they can explore the resulting object sets using the exploration view or view them as a table of results. Additionally, users can compare and contrast object sets and take bulk actions on the object set. I think I forgot what specifically an object set is. It's a set of objects. But I think there's more to it than that. I think that's where the interfaces things come in, I think. Anyway, then users can export the object sets or open them in a compatible application, such as Workshop. I don't know, I feel like I'm not getting much interesting stuff here. I mean, these are just, showcases, basically. I don't think I'm interested in that right now. Yeah. Okay, ontologies. Actually, you know what? I'm gonna call it. It's about to be 11 p.m. My brain is, well, my brain wants to not be looking at a screen right now. So I think we'll grant it that wish. Yeah, so mostly we did the most important thing, which is show up and go through some chapters of the Lingua Franca manual. We will resume tomorrow, hopefully. Yeah. Thank you for watching. If you found this interesting, please do like and subscribe, leave comments. Yeah, have a good night, good day, depending on when you're watching this, and I'll see you around.